Hello class, today we are on chapter 2 lesson number 3 and we're going to cover more on functions. And we have here uh, a runner in our illustration who ran a mile. His name was Roger Bannister and he was the first person to run a mile in less than 4 minutes. He did this in 1954 with a time of 3 minutes and 59 seconds. The table at the left shows how the record for the mile has changed in the past century. To picture the change, we can plot points corresponding to the pairs of numbers in the table on a graph. A graph in which the years and record times are the respective x and y coordinates of the points is shown at the top of the next page. So let's just take a quick look at the chart over here. We can see here on the left side we have the year, and we have what appears to be in 10-year intervals, 1870, 1880, 1890, all the way down to 1970. And we can see that the record time, how it changed from 4 minutes and 29 seconds all the way to 3 minutes and 51 seconds. Now on the other side, we take that same information and we're plotting points over here on this graph on the top of page 79. Okay, so let's continue reading on page 78. In lesson 1, we define the word function in the following way. A function is a pairing of two sets of numbers so that to each number in the first set there corresponds exactly one number in the second set. So you remember we made an x and y table, we did it horizontally, we did it vertically, and we understood that the y value corresponded to the x value just as much as the x value corresponded to the y. And in the previous lesson, we kind of did things in different ways to determine how to graph, how to plot, and how to find the formula for the function. In our example, the set of numbers is a set of years from 1870 to 1970, and the second set of numbers is the set of record times for those years. The record time for the mile is a function of the year because to each year there corresponds exactly one record time. If the two columns of numbers in the table at the left were interchanged as shown in the table at the top of the next page, the new pairing of numbers would not be a function because to the record time 4 minutes and 16 seconds there corresponds 2 years, 1900 and 1910. So we can see that they've actually placed an arrow or a couple of arrows pointing to the two different years, though it's the same time. So that would be a problem, wouldn't it? A convenient way to represent a function is with a formula. Not all functions have formulas, however. The relationship between the year and the record time for the mile, for example, is too complicated to have a simple formula. And even if we were able to write a formula for it, there would be no reason to expect it to work in the future. For a function that does have a formula, it is often useful to be able to graph that function. The most obvious way to do so is to 1. Use the formula to make a table, and 2. Use the table to graph the function. So we have an example over here. Now, just going back to what they're discussing, if you look at our chart with the plotted points at the top of page 79, you can see that these points are all moving downward because the time that it took to run the mile was improved upon. But we do not see any particular, let's call rhyme or reason. We don't see a correlation between the time passing and the change. In fact, the 1 year, 10 years passed and it didn't change. The record time was the same. So this is what they mean that not all functions have formulas. And again, as they said, this is very complicated. Some mathematicians spend lots of time taking complicated sets of data and they try to formulate a certain function or formula to those functions. But again, because it is so erratic, it's very difficult to point out and say, well, this is always going to happen. And in this particular case, obviously, because there is no particular constant, we cannot predict based off the previous information what would happen in the future. And now the reason we say that is because people try to use charts so that they can predict. Particularly, you may see a stock chart. It shows a particular stock, and one of the things that's very difficult, if anyone knew what would be the next price, let's say, the following day's price, well, a lot of people might be rich if they were able to predict that. But nonetheless, they still used charts to ascertain movement and what we would call maybe the probability of movement based on those numbers. Now, there's so many other factors that go into that. We don't want to go into it. But again, not every chart has a perfect straight line or a perfect curve to it. But when we do have formulas, there is now a predicted value because there is an absolute value that's going to be attached to it because something is going to equal something. So let's take a look at this example and explain a little more. Now we're going to have a graph that doesn't necessarily look like the ones we had before, but you will see that with the formula, and we're going to go ahead and write out our formula now. Probably need to change to my white pencil. No, I have it. Okay. So let's write out our formula first. We graph the function. Well, I do need the pencil, just didn't need the color. There we go. Y is equal to 9 minus x squared. Okay. Now we remember x squared, remember exponents, that would be x times x, okay? So we have y is equal to 9 minus x squared. So here we're starting to see a little more complexity in our formula. Before we might have had just x minus 9 or 9 minus x, but now we have an x squared. So that's going to behave in a slightly different way than the other charts that we were drawing and different formulas we were using. So solution is first we make a table of some numbers. So we're going to go ahead and put our x and y value. Remember, we can do this vertically or horizontally. We primarily focus on going horizontally in these first few chapters. So let's go with 0, let's go with 1, let's go with 2, let's go with 3, and we're going to go ahead and now plot these y values. What would y equal if x is equal to 0? Well, I would have to put this in, and let's use this side. We're going to say y is equal to 9 minus 0. I'm going to put the value in squared. Now, what is that? Well, what's that going to equal? Well, that's going to equal 0 times 0 is going to equal 0. So we have 9 minus 0. So the answer here is 9. So our value would be 9. Now, that's where they're getting their information from there. As you see, y is 9. Let's go ahead and do the next one. Y is equal to 9 minus 1 squared. Now 1 times 1 would equal to 1. So 9 minus 1 is going to be equal to 8. Okay, so now we have, so we went up 1 and we went down 1. So you're already seeing a pattern here. As this number's going up, this one's going down. But let's see what happens when we plug in 2. So we have y is equal to 9 minus 2 squared. Okay, so now we have 2 times 2, which we know is 4. 9 minus 4 is going to equal to 5. Okay, so we moved up another 1, but notice a change here. We dropped more than we dropped before. We only dropped 1 before, but now we've dropped 3. Okay, so something is different here. And we're not seeing the same rate of change. And it's really because we have to realize there's an exponent up here. We'll go further into detail down the road with that, but you're going to see that this is behaving different than that linear graph, that straight line where we were dropping maybe 1 and we were going up 1. This changed. And let's go ahead and try 3 now and see what happens. Well, y is equal to 9 minus 3 squared. Now 3 squared is 3 times 3, which is 9. So 9 minus 9 is going to equal to 0. So that's where we got all these numbers from. But now notice that it dropped 5. From here to here it dropped only 1, but over here it dropped 3, and now it dropped 5. So apparently this number is increasing. The difference is starting to increase. Now let's see what it looks like when we try to graph this. So we understand that our coordinates are now 0, 9, 1, 8, 2, 5, and 3, 0. Okay, and if we were to write these, I'm going to write them as we draw them. So I'm going to go and get my black marker. And it's going to be working on the graph here. So what's our first point? It's 0. So that means the x value is 0, means we move across horizontally first. Remember the x and y? Maybe I could have put here an x and put the y up here. Okay. So we have our x and y axis. So we're going to move 0, but we're going to go up 9. So that would be 1, 2, 3, 4, 5. Now, notice I had the 5 already written there. You can number every single one. When you start using a lot of numbers, you can just start spacing the numbers. You can do them in increments of 2, 4, 6, 8. You can do, say, 5, 10, 15. Depends on how far out you need to draw your graph. So in this case, we have 5, which is a nice point of reference because if I know that this is 5, I can just count from there 6, 7, 8, and 9. So our first point is going to be right here at the very top of the graph. So that would be point. And let me just put the value here, the coordinate. I'm just going to write it. I don't want to write it in the way where we're going to draw an actual line there. So our point is 0, 9, 0, 9, okay? So that's our first point. Now our second point is 1, 8. So we're going to move over 1 and count up to 8. Well, I know this is 5, 6, 7, and this is 8 over here, okay? So that's our next point, and I'm just going to put that value here, 1, 8, okay? So now let's go to our second, or third rather. We move over 1, 2, and now we're going to go up to 5, and we already know that that's right there. That's marked. So there's our 5. So that would be point 2, 5. Okay, and that's our coordinate. And lastly, we had 3 and 0, which means we move over 1, 2, 3, and now we don't move off that x-axis because vertically we're not moving. It's 0, so that would be right here, right lying on the x-axis, and that would be point 3, 0. Okay, so now you can see that we've plotted this, and let's see what they're saying here. It says next we plot the points whose coordinates are the numbers on the table, and we've done this. And the points do not lie in a straight line. Whenever this is the case, we will assume that they lie on a smooth curve. We finish the sketch by drawing in, we draw in the curve. So with your pencils, you do not want to do this, and this is very important. You do not want to draw, you're not connecting the dots, okay? You're not going from here to here. You're not drawing, I'm sorry, a series of straight lines. In fact, let me get my ruler or my marker here with the straight line. This is what we do not want to do. And let's change up our color. Okay, I do not want to see you do this and then connect a straight line to here, okay, and then connect a straight line. You see how that's kind of a straight. We do not want to do that because it really is not the true curve. Let's go back and let's try to do this by hand. I'll try to do my best. And what you're trying to do is just simply create the natural curve. If you see that we're going from, say, this point here, we're trying to catch that same slope. That's something else you're going to be covering over time. Oh, I'm sorry, that's not very good with this pen tab. Actually, it would be easier if I drew it coming across the other way. So let me just move my tab here. Okay. So it's kind of curving downward. Okay. And you see how I got a little curve on there, okay? Oh, I'm sorry. You're going to have to be patient with me on this one. I'm sure you're going to have some of the same struggles trying to draw this. I'm doing it on a graphic tablet, and I can just tell you it's a great challenge. If you can draw with these things, well, you've done quite a bit. Nonetheless, you can see how my imperfect curve is still a curve. It's sort of curving, and it's very important to note because it's not a straight line from point to point. So, and I'll just give you a hint that because we had an exponent here, that's what's creating this curve, because we're going to go later on into exponents and explain more of the impact of exponents and how it changes a formula. But in this case, we just wanted you to see that there's a curve here, okay? And And one other thing is that I want to explain, though we're not covering it in the book, that every single one of these points in between are actually values themselves, okay? Now we have chosen what would you might call a domain. Maybe we say we're just going to use whole numbers. So we're using 0, 1, 2, 3, okay? And so we're only using the whole numbers. We would only plot the dots. But if we're saying anything could be the answer, and truly anything can in this particular case, anything that, let's say, well, what if I replaced I put 1.5, okay? Well, 1.5 would be squared. You would subtract that and it would yield a result. It would be a decimal. And those decimals pretty much lie in between these whole numbers. So we have 5, we have a 6, we have a 7, we have an 8. And so they're numbers that are decimals or fractions in between. And to each y value, and there corresponds an x value, or x value, there corresponds a y value. So truly, every single point infinitely, because you could infinitely go smaller and smaller in between 2 points, all would be answers to this formula. So that's why we would draw the line. We'll go further into that in other lessons, but I just wanted to explain why we're drawing a line at this point rather than just putting the coordinate points, okay? So you can move on to your exercises, and that's the end of this lesson.